Welcome back to the Simpkins Physics Corner, coming at you from the crib here on a Wednesday night for some vector action. It might be at 9:30 on a Wednesday, my dudes, but we are ready to rock and roll. What is a vector and what is a scalar? Today is all about vectors. So if you have your body temperature, right, you have a temperature. Well, is that a vector or a scalar? Well, it's a scalar. It doesn't have direction. If I step on a scale, it would read 165 pounds. Not 165 pounds northeast. Doesn't have direction. It's a scalar. What about if you go on a paycheck, or you take your paycheck and you deposit into your bank account? If your bank account goes up, then and then it goes down, that can be positive or negative. That means it's either going up or going down. That would be a vector. So just a quick reminder of the difference between vectors and scalars. We also need to know about trig for this lesson here, so I'm going to do a quick review. There are three sides of a triangle as we define them when we do trigonometry, and the definitions of the sides all come down to what is the angle that we know. I'm already aggravated because my pen is not writing. Let's try this out. There we go. What is the angle that we know? Theta, right here. So the opposite side is defined as the side that's opposite the angle. Go figure. And then the adjacent side, of course, is the one that's next to the angle, and the hypotenuse is always the longest side. So we have to know those terms when we do our trig here today. Now, if I were to take one of my sweet Nerf guns here and shoot the dart up and to the right, like kind of up in the air, like pew, trying to launch it really far here, right? Let's say I read the box of the Nerf gun and it says the dart shoots 90 feet per second. All right, that would be telling me the velocity that comes out of the Nerf gun, 90 meters per, sorry, I'm so used to physics units, feet per second. It's an American box, what can I say? So the velocity in this direction is going to be 90 feet per second. But what about the up and the sideways motion? Because the dart is moving both to the right and upwards, right? And it's more convenient if we can break that overall quantity in a funky direction into the x and y axis. And so this is why we use trig when we're talking about vectors. This is all leading us into projectiles, by the way. So if I consider these sides, and I know the v, the velocity that the dart comes out, and I want to derive an expression for the x component, yx because it's horizontal. If I want to derive an expression for the x component, assuming that I know the angle I shoot it and the speed that I shoot it, how would that look? Well, let's use our trig. If you have a and h from SOHCAHTOA to help us remember that, SOHCAHTOA tells us that cosine of theta is equal to adjacent over hypotenuse. Cool. Now let's plug in the specific values we know. We know that cosine of theta is equal to, what's on our adjacent side? Vx. What's on our hypotenuse side? Over v. Now, if I want to derive an expression for Vx, how would I solve? I would have to multiply both sides by v. And what do we get? We find that the x component of the vector that is pointed along the direction of the hypotenuse here, that's the overall vector we call it sometimes, the overall vector v times cosine of theta of that angle is going to get us the x component of that vector. And usually we define angles as counterclockwise from east. If this direction is east or the positive x direction, we usually define the angle from there. So Vx would be equal to V cosine theta. Well, that means that Vy would be equal to V sine theta. And so if you're not a Pokemaster like me, this guy's named Psyduck. And what we know about Pokemon is that they can only say their own names, like Pikachu or Pika or Chew, right? So Psyduck can only say Psy or Psyduck. So he says Psy. He says Y sine. Why does it say Y sine? Because if you're looking for the Y component or the vertical component of a vector, you want to do Y sine. Vy tells you to use sine of the angle theta. All right, just a fun way to remember that. So let's apply this right now. What if I shoot something at 5 meters per second in a direction 30 degrees north of east? We'll get into what that means here in a second. Well, to find the x component, I would do V cosine. I would do the vector, the overall speed, 5 times cosine of 30. And I would get 4.33. And here it looks like it would be meters per second. Now, if I did the y component, I would use y sine. Oh, there it is. It's so fun to say. And if I did y sine, v sine equals 5 sine of 30, that would get us 2.5 meters per second. Now, if you know anything about angles, you know that this is 90 and this is 0. So 30 is kind of low like this. Look at that arrow. Is it pointing more up or more to the right? Answer, points more to the right. Look. It has a bigger x component, 4.33, than it does y component. Ah, okay, now I'm starting to see how this ties together. Now, when we're defining directions, sometimes we have to deal with stupid angles. Oh, there it is. All right, I thought you said west. You'll see this in textbooks all the time, and it's annoying. But here's what you want to do. Focus on defining your angle as counterclockwise from east. So east is defined as 0 degrees. Counterclockwise, for those who you can tell time good, would be in this direction. And so we want to define it as counterclockwise from east. That means that if I were pointed directly north, I'd call my angle 90. If I were pointed directly west, I'd call my angle 180. And if I was pointed directly south, I'd call it 270. And east, I could call it 0, or full circle, I could call it 360. So let's do a couple quick examples here. What if a dumb problem with a stupid angle said 40 degrees south of west? All right, here's how you interpret that. You start from west and you go south of there, because that's what it says. And we do that by 40 degrees. So think about that. If I went 40 degrees south of west, what number is that? Well, that would be 180 plus 40, right? And so that answer would get us 220 degrees, if I can do mental math well, which I can, hopefully. 30 degrees south of east. Well, here's east. So what if I go south of east by 30 degrees? Remember, east is defined as 0 or 360. And if I go 30 degrees backwards from 360, where am I? I'm going to be at 330 degrees. How about 20 degrees east of north? Ugh, gross. Why do they have to define it like that? But sometimes they do. 20 degrees east of north. That means you start from north and you go 20 degrees this way. Well, if I go 20 degrees that way and north is 90, that would be 70 degrees. And then 70 degrees west of south. Why even do that? All right. But I got to go 70 degrees west of south. If south is 270 and I go 70 degrees west of south, then guess what? I'm at an angle of 200 degrees. So keep an eye out for these stupid angles, I call them. I'm just always frustrated by the way that they define them. All right. So keep that in mind as a strategy. Now, when we add vectors together, because we can take a weird diagonal vector and turn it into horizontal and vertical components, we can add two vectors together by breaking them into their components, gathering up all the x components and adding them together, gathering up all the y components and adding them together, and then resolving it, we call it, into the overall vector. Let me give you a visual for what we're talking about. Let's say I wanted to add this vector down here, r1 plus r2. Now, the answer to that for the vector addition, the answer graphically would be from the beginning to the end. We call this the head to tail method. Why? Because this is the head of a vector, like an arrowhead, and this is the tail of the vector, just like the back of an arrow would be the tail, right? And so this would be how you would graphically draw the two vectors added together. And the resultant, or the result of adding two vectors together, that's the big R right there, is defined as from the tail of the first vector to the head of the last vector. And so the visual way to do this of adding r1 plus r2, the answer would be r, the resultant. But let's talk about how this informs us about our mathematical strategy coming up here. We know that r1 has two components. It has an x component and a y component. Y sign! There it is again. r2 has an x component and a y component. Now think about this for a second. What if I do a little trickery here? What if I know this is the answer I need to get, right? I know that the resultant should be from the tail of the first to the head of the last. Watch what happens if I move some things around. We've dissolved the vectors into their components. And what if I add the y components together and the x components together? What do I get? I get a right triangle whose hypotenuse is the resultant. So this is the visual for the strategy I'm about to show you mathematically. You're going to get two vectors. You're going to break them into their components. You're going to gather up the y's and add them together. You're going to gather up the x's and add them together. And then you're going to do the math for finding the magnitude of the hypotenuse. That would be the magnitude of our vector. And we can do some trig to figure out the direction or the angle that is going on down there. So if you get lost when we go here ahead to the math, circle back to this visual idea to keep in mind what we're actually trying to execute here. So a reminder, if we define our angle here from east, then it's y sine and x cosine. All right, so let's go ahead and dig into it. Let's say I wanted to add these two vectors together, 5 meters per second at 30 degrees and 6 meters per second at 70 degrees. So if I just had to do a rough sketch here, all right, we know it's like 90 and 0. So I got 5 meters per second at 30 degrees, something like that. Oh my goodness, my computer's freaking out here. There we go, like that. And 6 meters per second at 70 degrees. So that one would kind of be like this or something, all right, just to get the ballpark. The first thing you want to do, remember our picture that we just went through, the first thing you want to do is organize everything and break your vectors A and B into their x and y components. So that's why I set up the table the way I did. Look, this is telling us vector A's x component is going to be determined by its magnitude times cosine of 30. The vector B is going to be determined by its magnitude times cosine of 70. The y components of the vectors are going to be y sine. Oh, that's my favorite. 5 sine of 30 would get you the y component of vector A, and 6 sine of 70 would get you the y component of vector B. You might need to pause for a second to take this all in. But look, these are the y values, and these are the x values for vectors A and vectors B. It's really helpful to set it up in a table like this. So let's do the math. We plug this into our calculator, and we get these numbers. All right. Now, where did these numbers come from? Down here. Well, if you're an astute observer, you'll find that it's the resultant. It's the result of adding them together. Adding what together? If we add the x components of vectors A and B together, we get the overall x component. Are you picturing what we just saw in the graphic earlier? If I add the y components of vectors together, guess what I get? The y component of the resultant. So now what I have is I have the x component of the resultant, and I have the y component of the resultant. Let's go ahead and finish this up to find the final answer, because the answer is, what is the resulting vector that we get? All right, so here's a couple of strategies for you guys as we move forward. What you want to do is, after you use the table to find the x and y components of the resultant vector, you want to sketch them. All right, now in this case, it's easy because both numbers are positive. But keep in mind, if I get a negative answer for x, which way is that traditionally indicated? That's traditionally indicated to the left. And what if I get a negative for the y? That's traditionally indicated down on our quadrant system, if you are a coordinate system. Now, fortunately, we have two positives, so we're just going to line them up like this. All right, so you want to draw a picture. Now, I have a little phrase. It's Pythag for the mag. You're going to use the Pythagorean theorem, a squared plus b squared equals c squared, to solve for that. So you're AP students. I'm not going to hold your hand through that, but a squared plus b squared equals c squared. All right, so you'd plug in one of your sides for a, the other shorter side for b, and whatever you got for c, you'd have to take the square root, and you get 10.34. So to get the magnitude of the resultant, you do the Pythagorean theorem. Get it? Pythag for the mag. And then you do inverse tan for the direction. I know that's a little bit of a stretch, but the direction right here is the angle that we want, right? So we need the opposite side and the adjacent side. Well, if we use O and A from SOHCAHTOA, that tells us to do tangent. So if you do inverse tangent of y over x, or in this case, 8.138 over 6.38, you would get 51.9. If you plug that in your calculator and you get the wrong answer, that's because you're in radian mode. So you want to hit mode, go down 2 to the right 1, and select degree. Make sure your graphing calculator is in degree mode. Let's look at another example here. Here's what I'm going to do. I'm going to put this example up on the screen. I want you to pause the video. I want you to set up this problem, and I want you to do it. And then I want you to unpause the video and come back and look at what the answer is. You ready? Here's the craziness of the answer. Sorry, I shouldn't have gone there yet. All right, because what I just said is set up this table to help you out. All right, so you can set up this table to help you out. You're adding 3 vectors together. It's getting nuts, right? But here is the answer, so you can pause the video again to check your work, to check your answer. It's a beast, and I can only make my videos 15 minutes, so I want to make sure that you guys have enough time to get all the stuff that you need. All right, here's all the info you need. Hit me up with some questions in the comments if you lost me somewhere. Let's finish this one up here today. All right, what if we have a boat that goes across the river? So the boat's speed is going to be determined just by how much its motor is pushing it, right? But there's a current in the river, and that current is going to move the boat in one direction or the other. All right, so the question here says, what's the resultant velocity of the motorboat? That first one's easy because we know how to do resultants. If we have 4 meters per second east and we have 3 meters per second north, some of y'all know that a 3-4-5 triangle is one of our things we know from trig. So the resultant velocity would be 5 meters per second. Now, remember, velocity has a direction, so we should also go ahead and solve for that angle there. We can use inverse tan for the direction. So if I do inverse tangent of 3 over 4, that would get me the angle or the direction for that. And if you plug that into your calculator and you're in degree mode, you get 36.86 for the direction. So actually our full answer for velocity would be 5 meters per second at 36.86 degrees, indicating our direction. Now, if the width of the river is 80 meters wide, so this is 80-meter wide river here, then how much time does it take the boat to travel shore to shore? Here's where things get interesting. I have 1 minute left. If I have a motor pushing me at 4 meters per second, you're like, but Mr. Simpkins, the current is also pushing you upwards, right? The current is also pushing us upwards. Does the current change my horizontal speed? Answer is no. All right. So actually, the only information I need to find this time is I know that velocity is equal to displacement over time. And the amount I'm being displaced horizontally is 80 meters. and I'm trying to find the time, and that would be equal to 4 meters per second. So I do a little algebra. I swing the t up, bring the 4 down. I got 80 meters over 4 meters per second would get me, oh, I'm doing this too fast, 20 seconds. Now, what distance downstream did the boat reach the opposite shore? That is where the velocity of the river would come into play. I want you to keep this phrase in mind as we move into our next lesson. The motion in two directions is independent, happens at the same time. So it's independent, but it's simultaneous. Keep that